Good morning, Missy.
Good morning, class. I'm Miss Ian. Today I'll be showing you guys an examples of finding area using integrations. So this is the diagram. So in this diagram, you can see that the two shapes looks very similar. In fact, they are the same. The shapes are the same, and the area also the same. But the way to find this area, the method will be totally different. So today I will be showing you guys the method to find the area to each of this diagram. So let's start with the diagram at the left side. Okay, this is a diagram that is shown in the previous slide, the left side. So in this diagram, there's equations given here. And in order to find area, guys, please remember that whenever you want to find area that involve two graphs, intersection point is very important. No matter the question, no matter the intersection point is asked in the questions or not, you always need to find that. So these two intersection points, these 2 points, we can find these 2 points by doing simultaneous equations, since the equations are given here. So I will just put them equal, since both equations also in a subject as y. So we have x minus 3 squared equals to this. And I will bring this to the other side, then we will have plus x minus 3 squared equals to 8. And we can choose not to expand this. As you can see, we have x minus 3 squared, and then the other one also x minus 3 squared, so we can add them together and put 2 times of x minus 3 squared. And I can just solve these equations without expanding. What I mean is, I can just bring 2 over 8 divided by 2, then I will have 4. And we just need to find the square root of 4. So square root of 4, there are 2 possible values. So it's either positive, the square root of 4, or could be negative square root of 4. Then we will have 2 plus 3, which is 5. Another one is negative 2 plus 3, which is 1. So these are the x-coordinate of the intersection point. So the next thing I'm going to do is, doing these steps also very important. What am I going to do is, from this intersection point, I will draw a line down to the x-axis to mark the x-coordinate of the intersection point, which is 1 and 5. Okay, the next thing that we need to figure out is which part of the area actually we are finding when we do integrations on this graph. So for this diagram, I have put these 2 graphs into separate diagram to figure out the area that we are finding when we use these equations. Each of these equations, when we use them to do integration, which part are we finding? So this graph, we have found the intersection point, which is 1 and 5. So I will mark the point here, 1 and 5. Student, please bear in mind that when you do integrations to find area, the area that you are finding is actually between the curve and the x-axis, provided you are doing integrations y dx. You're actually finding this part. Okay, from 1 to 5, this is the part you are finding. It's between the curve and the x-axis when you're doing integration y dx. That is for this graph. How about the other graph? Okay, let me write down the intersection points. So we have 1 and 5 here. So when we use this graph to do integrations, the area that we're actually finding is again between the curve and the x-axis. What I mean is, between this curve and the x-axis when you do integrations from 1 to 5 using the equation of this graph, 1 to 5. This is the part we are finding, which I put in pink. Okay, so now do you guys Can you guys figure out what do we need to do with the area that I put in yellow and the area that I put in pink? What do we need to do with this to get the green shaded area? Can you guys see that we actually need to minus? If you still cannot see, what I can do is I will draw this graph here and put in dotted graph. This is the graph that is drawn in a separate diagram. And we have already figured out that when we do integrations on this dotted graph, the area that we are finding is this part. The area that we are finding is this part. So can you guys see that we have to use the yellow region to minus the pink region in order to get the green region? Okay, so now we start with the integrations. So let me draw a line here. So for this part that I highlight in yellow, we have to use the equations. We have to use the equation, these equations. These are the equations to this graph. So we have to use this in equation to do integrations. So integrations 1 to 5 and y dx. So I'm going to put negative x minus 3 squared plus 8 dx. And minus the pink region. Pink regions, the equation we have to use will be this. This is the equations for this graph. So minus integrations 1 to 5 and these equations. Okay guys, since we have the same limit, you can see that this is integration 1 to 5. The other integrations also 1 to 5. We can combine them. Instead of doing them separately, we can combine them and do integration together since they have the same limit. So the next thing I'm going to do is integrations 1 to 5 negative x minus 3 squared plus 8 minus this. And as you guys can see from this, this and this are the like term that we can simplify. Then I will put this as 8 minus 2 times of this. Okay, can you guys see that I have actually combined this and this become this. And 8 I just copy. So next we just use the formula for integration. So integrate 8 is 8x. And integrations on this. So remember integrations power increased by 1. So power is 2 increased by 1. Then divide by the new power, which is 2 plus 1. And don't forget to differentiate inside. Differentiate x is 1. And differentiate 3 is 0. As this is a definite integral 1 to 5, so it's not necessary to put constant. It's not necessary to put plus c. Integrations 1 to 5. Then by simplifying this, we will have 8x minus. So 2 is the numerator. 2 plus 1 is 3 that I put here. So after that, in order to find this area, we will need to just put 5 and 1 in. So next steps, we just put 5. So guys, please remember for definite integral, you have to put this top number into x first, and then followed by the bottom number. Okay, and what we need to do with this 2 is minus. Okay, this is what you need to do for definite integral. So I will put down the answer here. So this, if you type in everything in the calculator, the answer will be, let me write down this also. For the first substitutions, if you try to use your calculator and key in this, for the first substitutions where you substitute 5, you will get 104 over 3. For the second substitutions where you substitute 1, you will get 40 over 3. Then the final answer will be 64 over 3 square unit. This is the area to this diagram. Okay, for the other diagram, which is the diagram at the right. Okay, let me share with you guys. Okay, this is the diagram. So to find this area, like what I showed you in the previous questions, the diagram, intersection point is very important. So happen that for this diagram, the intersection point also the y-intercept. So instead of using these two equations to do simultaneous equation, I can actually use one of these equations to find y-intercept. It actually gives us the same point. So I will just use this x minus 3. Okay, y equal to this. So to find this point, which is the intersection point, and they're actually the y-intercept. So everybody should know that for y-intercept, it's x-intercept, it's x-intercept. So everybody should know that for x-intercept, y equals to 0. So y equals to 0. So we just solve these equations. Again, you can choose not to expand this. You can just bring 4 over and then find the square root of 4. Then we will have two possible answers again. It could be positive 4, or it could be negative square root of 4. Then we will have 2 plus 3, which is 5. And then for this will be negative 2 plus 3, which is 1. So we have 1 and 5. These are their x-intercept. If you are thinking to use the equation, these two equations to do simultaneous equation, you definitely get the same answer. But I would think that using x-intercept this way will be faster and easier. So next thing, do you remember what do we need to do? After finding the intersection point, the next thing is you have to figure out the area that you are finding when you use each of these equations to do integration. So I separate this two graphs into two separate diagrams. So for this graph, okay, let me mark the intersection point, which is 1 and 5. Okay, guys, if you use this graph to do integrations 1 to 5 y dx, which part of the area we are finding? Remember, it's always between the graph and the x-axis if we are doing y dx. Between the graph and the x-axis. So this is the area we are finding. Okay, how about the other graph? When you do integrations of 1 to 5 again, y dx. Okay, I think I need to mark 1 and 5 here, the intersection point. So if we are using these equations to do integrations 1 to 5, I think most of the students always like to use area under the curve. So when you use these equations to do integrations, are you really finding area under the curve? What is area under the curve? Do you think that the area that you are finding is actually this area? Since it's under the curve? It's not. It's not this part that you are finding when you do integrations. So guys, please remember, that's why sometimes I found that area under the curve, this phrase is not really accurate. So actually, the area that we are finding when we do integration is always between, mark my word, between x-axis and the curve. This is the area we are finding instead of area under the curve. It's between the curve and the x-axis. So can you guys see that what do I need to do with the yellow regions and the pink regions to find the green region? Now we need to do plus. But in the previous diagram, we need to do minus. Can you guys see the difference now? So let me draw a line here. Okay, so for this yellow regions and the equations to this graph will be this. So I will need to use this to do integrations of 1 to 5. Negative x minus 3 squared plus 4. And then for this pink region, the equations that I will need to use is this one. So plus this, and the same limit, 1 to 5. like in the earlier example, since I'm doing integrations for the same limit, I can actually combine them instead of doing them one by one. So next thing, what I will do is combining these two. Oh yeah, one more thing. Yeah, I forgot to tell you guys. Do you guys know that when you do integrations, the second part, the area that you are finding is actually negative because it's below the x-axis. This area will be in negative. So if you just leave it in this form, then you are actually finding a positive area plus negative area. Then this calculation will be we are finding a yellow regions minus the pink regions, which is not supposed to be the solution. In fact, we should do plus. So what we need to do is we have to insert a modulus absolute value, which means we'll only take the positive value, because these calculations, this solution to this will give us a negative value that we need to remove negative to get the positive. Else we are using the yellow region to minus the pink region. So in this case, I will rather not to combine them. I will just find the integrations one by one. Okay, so for this, I will have negative x minus 3 and power increased by 1, then I will have 2 plus 1 over power 2 plus 1, the new power, and differentiate inside is 1, and integrate 4 is 4x. So this integration, we need to insert 1 and 5. And then plus modulus. Okay, these integrations, we use the same formula, which is power increased by 1. So we just put 3 over the new power, and differentiate inside is 1, and integrate 4 is 4x. And we need to put 1 and 5. So the next thing what we have to do is we just insert all this 5 and 1. So I will have 5 minus 3 to the power of 3 over 3 plus 4 times 5. This is what I get when I substitute 5. And then you need to substitute 1 as well. Then you have 1 minus 3 over 3. And then 4 times 1. And you need to do minus. Guys, I know the working is very long. This thing is actually only for this. So we still have another one need to calculate. So that we have to add the modulus, okay, of when you put in 5, power 3 over 3 minus 4 times 5. And then followed by substitutions of 1. Modulus of this value. So this whole thing here is actually for this. Okay. So there's an equal sign here. So then the next step, so this 2 line of working is actually one step. This 2 line of working is actually one step. So we need to use this minus this to get a value. And then you add another value, which is a modulus value. If you key in this whole thing in the calculator, you get negative value, and you need to remove that negative. So if you key in everything, then you will have the first substitutions, which is 5, you will get 52 over 3. And then the second substitutions, when you substitute 1, you will get 20 over 3. And then plus the modulus. So when you substitute 5, the things you will get is negative 52 over 3. And minus this will give us negative 20 over 3. So this will be 32 over 3 plus modulus of, you key in this thing in the calculator, you get negative 32 over 3. So let me write down the next step here. 32/3 plus, since we know that modulus, we have to remove the negative. So in the end, the answer is 64/3. So square unit. This is the answer to this diagram. Okay guys, I hope you guys find this very useful. These are the different way of finding area for different diagram. Please remember, when you use integration to find area, we are finding the area between the curve and the x-axis instead of area under the curve. I hope you guys find this useful. And if you guys have any other topics that you would like me to share with you guys, please leave your comments below. I see you guys next time.